understand thermodynamics, we must first understand energy. Energy is present in any chemical reaction. For example, the bonds between atoms contain energy. When energy is absorbed, bonds are broken, and when energy is released, bonds are formed. Essentially, chemical reactions are the change in energy between the products and the reactants. This transfer of energy is called heat, which is the basis of thermodynamics. Thermodynamics is how heat interacts with other forms of energy. Enthalpy is also an important concept to understand. It is the stored chemical energy, or in other words, the heat content of a system. When calculating enthalpy, we must find the change in enthalpy, because we can determine the zero point or initial enthalpy of a whole system. Let's visualize this concept.
Imagine there is a firefighter that is partially way up on a ladder. Let's also consider the rungs on the ladder as increments in enthalpy. Now, because of the smoke, the firefighter can't see the bottom, so they can't tell where zero height is. But the firefighter does know that he needs to climb 3 more rungs to reach the window of the burning building. So, in order to reach the window, the firefighter doesn't need to know the height above the ground, but he does need to know the difference in height between him and the window, which in this case is 3 rungs. In terms of thermodynamics, reactions can be classified into 2 types: exothermic and endothermic reactions. Exothermic reactions release energy, therefore their change in enthalpy is negative. Endothermic reactions absorb energy, therefore their change in enthalpy is positive. Let's look at the energy diagrams for these reactions. In an exothermic reaction, the reactants start with high potential energy. As the reaction occurs, energy is released, therefore the products end with low potential energy. In an endothermic reaction, the reactants start with low potential energy. As the reaction takes place, energy is absorbed, therefore the products end with high potential energy.
Another crucial concept is that of calorimetry. Calorimetry is used to measure the amount of heat transferred to or from a system. In calorimetry, we use the following formula: Q equals mc delta T, where Q is the heat transfer, m is the mass, C is the specific heat capacity, and delta T is the change in temperature. Let's assume we have 2 substances in a closed system. Substance H is hot and substance C is cold. We can assume that the heat transfer of substance H equals the negative heat transfer of substance C, because the heat lost by H is equal to the heat gained by C. Let's look at an example.
Suppose that you want to make a cup of coffee that has a temperature of precisely 65 degrees Celsius. You start by making 250 milliliters of coffee at a temperature of 80 degrees Celsius. In order to cool down the coffee, you add milk that has a temperature of 5 degrees Celsius. The question is, how much milk do you need to add in order for the coffee to be at your desired temperature of 65 degrees Celsius? Let's begin by assuming that the density of both the milk and the coffee is 1 gram per milliliter, and that the specific heat capacity of both liquids is 4.184 joules per gram per Celsius. Since cold milk is added to the hot coffee, we can assume that the heat transferred from the coffee is the same as the heat absorbed by the milk. We can represent this idea using the following mathematical statement. Q represents the heat transferred. This equation can be rewritten. Once we have the MCAD equation, we can plug in our known variables. Notice that the mass of the milk is left as a variable. We can then solve the equation. So, the amount of milk needed to cool down the coffee to 65 degrees Celsius is 62.5 milliliters.
Previously, we discussed what is enthalpy and why we measure enthalpy change. Now we will discuss how to determine enthalpy using a concept known as Hess's law. This law states that the enthalpy change of a reaction depends only on the enthalpy change of the products and the enthalpy change of the reactants. Essentially, we disregard the path of the reaction and only look at the initial enthalpy change and the final enthalpy change. We can visualize this idea using the following. Let's say we have a reaction that goes from A to B and has an intermediate step of C. We will call the enthalpy change from A to B delta H1, as it is the enthalpy change for the whole reactions, since it goes from the reactants to the products. We'll call the enthalpy change from A to C delta H2, and the enthalpy change from C to B we will call delta H3. Using this model, we can write the following equation, where delta H1 equals delta H2 plus delta H3. We can actually rewrite this equation as the following, where delta H for the whole equation, for the whole reaction, equals the sum of the delta H of the products minus the sum of the delta H of the reactants. Now let's look at some examples. So, in this problem, we will use the model we just saw to determine the delta H for this reaction between from carbon to carbon monoxide. We are given the delta H from carbon to carbon dioxide, which is negative 393 kilojoules per mole. And we're given the delta H from carbon monoxide to carbon dioxide, which is negative 283 kilojoules per mole. We can write this reaction as the following, where negative 393 equals delta Hx plus negative 283. Let's rewrite this equation, leaving delta H on the left as the following. Now, when we have a minus and a minus, we know we can add. So, the unknown enthalpy, the unknown change in enthalpy would be negative 110 kilojoules per mole. Let's look at another example. In this specific problem, they want us to determine the change in enthalpy of the reaction shown above using the following information. We're given three equations and their change in enthalpy, and asked to find the change in enthalpy for this equation. So, the best way in going about to solve this problem is manipulating the three equations to fit our desired equation,
And by doing so, we will manipulate their delta H's. After that, we can add up the delta H's to determine the delta H for this equation. So, let's begin by rewriting these equations. Okay, now that we've rewritten the information, we can start playing around with it and seeing how we make it fit our final equation. So the first thing I notice in equation 1 is that NH3 is on the reactant side and we want it to be on the product side. A simple way to fix this is by reversing the equation as the following. We would change the direction of the arrow like this, and by doing so we would also inverse the enthalpy change. So from a positive it would become a negative. Looking at the second equation, we can do the same. In our final equation, NO2 is on the reactant side, and here it's on the product side. Let's do the same and reverse the sign. And by doing so, we would change this from a negative to a positive. Before we go on to our third equation, we can start canceling some things out. If we see here, NO2 is on the reactant side, and here it's on the product side. So we can cancel it out. And finally, we can see that we do not have any oxygen in our equation, so we need to find a way to cancel out these two oxygens. We already see they're on opposite sides of the equation. This oxygen is on the product side, and this oxygen is on the reactant side. But this has a coefficient of 2, and this has a coefficient of 1/2. So we can multiply this whole equation by 4. When we multiply by 4, we'd also need to multiply the delta H by 4. Let's put this here so we won't forget. So now we'll get 4 here. We would get a 2 here and a 4 here. Now that this is done, we can cancel out this O2 and this O2. Now, let's write our equation again, looking at all the information we have. Let's begin by looking at the reactant side. We have 3 H2s here and 4 H's here. We can rewrite this as 7 H2 plus our 2 NO2 here gives us 4 H2O here on the product side and 2 NH3. And this matches our desired equation up here. So now we can add up these delta H's after manipulating them, and we can see that the final enthalpy change for our desired equation is 228 kilojoules per mole.